You might have first heard about modular arithmetic as clock arithmetic. We say that A and B are equivalent mod n if A and B represent the same time on an n-hour clock. So 17 and 5 are equivalent mod 12 because both are 5 o'clock on a 12-hour clock. One way to see if two numbers are equivalent is to ask, well, what time would a clock show for each and see if they're the same. So are 11 and 25 equivalent mod 7? Well, on a 7-hour clock, 11 would show up as 4 o'clock, and 25 would show up as 4 o'clock. Since they're both 4 o'clock, they are equivalent. 11 and 25 are equivalent mod 7. And that's the most common intuition, the fastest way to explain what it means for two numbers to be equivalent mod n. But in a discrete math class or a number theory class, they'll give you a formal definition. They'll tell you that A and B are equivalent mod n if n divides b minus a. And divides just means goes into evenly. So for example, 3 divides 12 because 3 goes into 12 exactly 4 times. You can break 12 up into exactly 4 groups of 3. But 3 does not divide 16, for example. You don't get an integer when you divide 16 by 3. So these two ideas, idea 1, look at the clock times and see if they're the same. And idea 2, ask, does n divide b minus a? These ideas look very different from each other. Right, so do these definitions actually mean the same thing? It turns out they do. And in the rest of this video, we're going to see why these definitions always match. Let's compare 11 and 25 mod 7 again. We saw they were both 4 o'clock. What happens when we apply that second n divides b minus a meaning? Well, let's run the clocks again and make a square for each hour that elapses. So for 11, we'll go around the clock 1 full revolution, that's 7 hours or 7 blue squares, and we'll have 4 left over. That's the 4 orange squares, and why it's 4 o'clock. Right, let's arrange those squares and then remember what they look like. And then let's do the same for 25. 25 is 3 full revolutions, that's 3 different groups of 7, plus 4 left over. That's again the 4 orange squares and 4 o'clock. All right, let's arrange those 25 squares in the same way as before. Now we're ready to check the definition. The question is, does n divide b minus a? Does 7 divide 25 minus 11? Well, 25 minus 11 is 14, and 7 does divide 14. And that's not a coincidence. What happens when you subtract? Well, the remainders, those 4 o'clocks, those 4 orange squares, those are going to cancel with each other. And 3 full trips minus 1 full trip, it's going to give you 2 full trips around the clock left over. So does the number of hours divide b minus a? Well, yeah, it's exactly 2 full trips around the clock left over, 2 groups of 7. 7 divides 14. And as long as you have just full trips when you subtract, the number of hours is going to divide that difference. So when the clocks show the same time, n does divide b minus a. But to be really sure the definitions match, we need to make sure they work the same way when the clocks show different times too. So n should not divide b minus a when the clocks show different times. All right, so let's see an example like that. We'll check 24 and 9 mod 7. Let's start with 9. That's 1 full trip with 2 left over. It is 2 o'clock on the clock. And now 24, that's 3 full trips with 3 left over. It's 3 o'clock on the clock. And so with the clocks, we got 2 different times, 3 o'clock and 2 o'clock, 3 orange squares with 24 and 2 orange squares with 9. When we check the formal definition, when we subtract, we get 2 full trips plus 1, 15. Does 7 divide 15? Well, no, there's one left over. That's the one orange square, the 3 minus 2, the difference in the remainders. Because the clocks showed different times, we have something orange left over. And that orange thing is not going to be a multiple of 7. It's not going to be a full trip around the clock. So n cannot divide b minus a. 7 is not going to divide 15. And that's why these two definitions, your clock intuition and the formal definition, match. We can match up the full trips with each other and the remainders with each other when we subtract. If the remainders, the clock times, the orange squares, match, then full trips of n hours each are all that's left, and n is going to divide b minus a. When the remainders aren't the same, there's something orange left over when you subtract, and n is not going to be able to divide b minus a because you'll have the orange squares left over. And that's why these definitions really do always mean the same thing.